Picture a small materials R&D team on a Monday morning. They have a mandate to find a new high-performance polymer, and they are staring down a list of thousands of untested chemical possibilities. Synthesizing and testing a single chemical compound requires physical lab time, expensive raw materials, and human labor. Every incorrect bet drains their highly constrained experimental budget and burns precious runway. Where does all this candidate data actually live? Mostly in disconnected spreadsheets, conflicting manual notebook scribbles, and isolated candidate lists scattered across local hard drives. Materials research hits a wall when teams can't move past the top-line data. Without a structural mechanism to rank these candidates, there is no way to know which molecule actually deserves lab time. Enter Discovery Intelligence. This is a workspace-scoped candidate prioritization workbench built exactly for this problem. Moving a team from random, disorganized guesswork into a rigorously tracked decision lifecycle is the mandatory first step before any deep scientific reasoning can take place. The workflow starts when a researcher uploads a massive, unstructured raw CSV file packed with candidate molecules. The system immediately locks this raw upload inside a strict session boundary, establishing clear workspace ownership. The upload parser then actively scans the dataset, throwing out corrupted rows and duplicate entries. Surviving molecules pass through RDKit for canonicalization, forcing them into a standardized, machine-readable format. By enforcing this intake boundary, the platform ensures that all subsequent modeling is performed on standardized, interoperable data. It removes formatting noise before the first calculation begins. You cannot run deep predictive modeling on thousands of molecules instantly. Trying to force heavy scientific analysis into a standard web request will block the thread and crash the interface. Through asynchronous orchestration, the session becomes an independent task moving through a background thread. A calibrated random forest pipeline calculates base success probability and assigns statistical confidence scores. Simultaneously, a Tanimoto similarity analysis compares candidates against reference chemistry to measure structural novelty. Running the data through these distinct analytical layers takes a flat list of chemicals and converts it into a mapped landscape of calculated scientific risk. If you sort a spreadsheet of molecules from the highest score to the lowest and synthesize the top 10, you will likely miss your best discoveries. A pure top-to-bottom ranking ignores the balance of risk and reward. Discovery Intelligence applies a portfolio allocation strategy instead. Candidates are divided into 3 strategic buckets: exploit for highly confident bets, learn for informative uncertainties, and explore for high-risk novelties. These lanes are mathematically balanced, ranked internally, and compiled into a single immutable decision artifact. Finally, this structured artifact is routed directly to the human review workbench. Here, the scientists take over. They inspect the explanations, review the chemical structures, append their workflow notes, and make the final approval on what moves to the lab. Discovery Intelligence connects the initial upload directly to the final synthesis list. This allows the R&D team to focus their effort on executing a high-confidence experimental strategy rather than manually auditing CSV files.